Unit Operation Classroom, Gate 2023, Question 22. A slab of thickness L, so this is my slab of thickness L, as shown in the figure, has cross-sectional area A. So this cross-sectional area, this is my cross-sectional area. So this area is my cross-sectional area. This area is A. And a constant thermal conductivity of K. So this is a constant thermal conductivity. T1 and T2 are the temperatures at x is equal to 0. So this is my x is equal to 0 and this is my x is equal to L. So here is the temperature T1 on this face and T2 on the temperature on this face. Which one of the following options is the correct expression of the thermal resistance for steady state one-dimensional heat conduction? We know from the Fourier's law of heat conduction, this is the equation here. Now, let's look at the resistance from the electrical circuit point of view. See, if this is the potential difference, so this is the current flowing to a resistance here. Okay, so resistance is defined by Ohm's law according to this equation, where this is the potential difference, is the current. Now, the analogous one for thermal resistance is, we say, so for this is the temperature difference. So this is my the potential difference, and because of the potential difference, there is a flow of current to the resistance. So similarly, because of the temperature difference, there is a flow of heat through this slab, and the equivalent of current is the heat flow rate. So here the potential difference is the same as the is equivalent to this temperature difference for thermal resistance, and equivalent of the current is the heat flow rate. Okay, so this is T1 minus T2 divided by Q. So this is the driving force divided by the flow of heat. This is my driving force divided by the flow of heat. So this is my thermal resistance. And if we look into this equation from here, so therefore the thermal resistance would be L over Ka. So T1 minus T2 Q dot comes over here. So the thermal resistance is L over Ka. Okay. So thermal resistance for this system is L over Ka. So therefore A is the correct option. Now you can stop the video if you are interested in the answer to this question. But next I'm going to discuss some applications of these thermal resistances. First of all, let's see how just like the current, we have the resistance can be series, or this can be series. So this is my series resistances, or the parallel resistance, if you remember, something like this. So this is the voltage here, and this is my parallel resistances. Okay, if you remember those things. Okay, so similarly, what will be the equivalent for thermal resistances? Let's say there is a high pressure steam line, carbon steel pipe with insulation, which is very common for refineries and fertilizers. So here the resistances are in the series. So resistance are in the series. So this is my the resistance of the pipe, then the resistance of the pipe, then we have the resistance of the insulation, and then there is a resistance to heat transfer from this insulation surface to the outside ambient air. Okay, so total resistance is, of course, resistance of the pipe, which in any textbook these are given here. So this is, let's say, the pipe, and this is the internal radius, and R2 is the external radius. So the thickness is R2 minus R1. And let's say this is the length of the L of the pipe, or this could be done in terms of unit length of the pipe. And similarly for insulation, so here this is equal to R2, and insulation is here, so this is R2, and this is here R3. Okay, so for the insulation layer, this is the thermal resistance, and for the ambient convection, so this is my thermal resistance. So as you can see, this resistance is in series, but thermal resistance in series. And of course here would be the temperature inside here. So let's say this is my T1, and the temperature here T2. So if this should be here T1, inside the whatever is fluid is flowing to the pipe, and outside ambient temperature T2. So that's the way it is done here for series thermal resistances. And the same thing with, let's say, furnace wall with refractory bricks, which could be like FCC regenerator, reformer, cement kilns. We have resistances in series. In a fired heater, we know we have the dense fire brick. We have this dense fire brick here. Of course, this is cylindrical, but this could be something like this. So this is the fire brick, and after that we have the insulation. Then we have the steel shell right here, so this is the insulation. This could be the fire brick. Okay, and what we always do, our total would be equal to all the resistance summation of each layer of thermal resistances. That's the way we do the calculation. Let's say for heat exchanger in tube wall with fouling. So we know that this is a very standard equation where HI and HO are the inside and outside heat transfer resistances. I mean heat transfer, convective heat transfer coefficient. Now this is 1 over HI and 1 over HO are the inside heat transfer resistances. HI AO, okay, and so this is the inside and outside resistances, and RFI and RFO the inside and outside fouling resistance of the tube. So these are the fouling resistances of the tube, and this is the resistance offered by the thickness of the tube itself. So here, let's say this is a liquid flowing through it. So, and this is the thickness of the wall of the, let's say, steel tube. So here there is a inside thermal resistance, and the resistance to flow through this tube, and of course then the resistance to flow outside of the tube, and there is a fouling here and there's a fouling here. So basically there's inside and outside fouling resistances. Okay, so that's, so you add up all the resistances. These are resistances added in series. There's a common simplification. We do the resistance based on outside area. So this overall resistance would be equal to. So this is the equation again, which is given in a standard textbook. Also, we see that RF, which is the sum of the inside and outside fouling resistances, is given as RFO plus RO over RI. So you just do that, RO over RI. So RFO plus RO R5. This is called the sum of the inside and outside fouling resistances. Okay, and this is for the inside liquid, and this is for the outside air, and this is the resistance due to the tube, which is normally very, very small because K is very high thermal conductivity. So common simplification, what we do, see, if we take this equation here, we can say this one and plus this one, this is what we call is the RF, thermal resistance due to the fouling, and this one and this one and this one, this is the clean overall resistance, which is due to the outside air. This is through the tube, and this is the info due to at the interface of the inside liquid and the tube. So this one and this one and this one constitutes the resistance due to the clean overall resistance, and this one and this one and this one constitutes the fouling factor or dirt factor. So fouled overall resistance is equal to the clean overall resistance plus the fouling factor or dirt factor, and the values of this fouling factor and dirt factors for different combination of fluids are available in standard textbooks. Now let's look at the parallel thermal resistances. So let's say here we have this is a very standard jacketed reactor which is used in pharmaceutical industry. There's a heat loss to the cylindrical wall, and there's heat loss from the top and the heat loss from the bottom. So that's basically the parallel thermal resistances. So heat loss from different dimensions of the tube. So that's so basically this one right here. So in case of parallel thermal resistance, we know for the electrical parallel thermal resistance, so I total is equal to I1 plus I2 plus I3, that the current through different resistances, if you remember this one. Okay, so current through different resistances. So these are basically circuit of a parallel resistance circuit. And if R equivalent is the resistance, overall resistance due to this parallel circuit, so it's inverse of each resistances. Okay, so similarly for thermal resistances, we say their current and Q are equivalent. So basically we get Q total is the heat loss, let's say through this wall here, heat loss from the top and heat loss from the bottom. Okay, and the overall resistance is equal to 1 by R1. So resistance due to this tube wall, and the resistance may be due to the loss of heat from the top, and the resistance due to loss of heat from the bottom. This is the overall resistance. That's the way we do it. It's exactly the same concept. Let's take very quickly an example. Let us say this is my as a reactor, is a pharmaceutical liquid, and it's 2 meter in diameter, and the temperature of the liquid inside is 80 degrees Celsius, and the ambient temperature is 25 degrees Celsius. Let's say this tube is 3 meter long. Okay, 3 meter long, and the inside there's a liquid inside, so this is some kind of pharmaceutical liquid. The heat transfer coefficient is 500 watt per meter square Kelvin, and the outside air, so this is losing heat to the outside air, is that's very low, that's 10 watt per meter square Kelvin. Okay, let's see here, this one, there's an insulation here. There's first the wall thickness. So because of the wall thickness, of course this is very high thermal conductivity. Let's assume the wall thickness is 0.006 meter, and the thermal conductivity of the steel is this 16 watt. And then after that there is an insulation. So after that there's an insulation here, so that's basically, let's say, 0.05 meter insulation, and this is the insulation thermal conductivity. So these are of course heat losses parallelly. Okay, for simplicity we assume this something like this. Okay, so here there's a heat loss to here. This is a flat one, and its area is pi d square, pi s square, so basically 3.14 meters square, and this one is pi dl, that's 18.85 meters square from the surface heat loss from here. And the top one is of course 3.14 meters square, and the bottom one also 3.14 meters square. We are assuming, making an assumption, so something like this. Okay, so the resistance for any particular circuit is basically for the inside film. Then we have the steel, whether it's top or here, that's for the steel, the resistance due to the steel, then the resistance due to the insulation, and then the resistance to the outside film. So for the heat transfer resistance from here, as you can see, this is 500, which is this one 1 over HA. This is the area, and this is the thickness of this one right here. Okay, steel wall, and that's a K 16 here, and that's the area 18.85 meters square. Similarly for the insulation, and similarly for the outside air. Okay, and that is the resistance due to heat transfer along this direction. Okay, similarly we can find out the heat transfer from the top plate. Means let's assume the heat transfer here. So what we have here is so heat transfer resistance from the top plate would be equal to 1 over 500. Now the area changes, but this this remain the same. The areas change here. These values remain the same. Okay, just the area changes, so 0.43 kilowatt. And similarly from the heat transfer from the bottom plate is these things remain the same, except only this one right here, because here we are assuming the outside air heat transfer coefficient is slightly lower than from the top, because this is kind of like cramped here. So this 0.43, 0.46. So what is the overall resistance? The overall resistance is due to what is going out from here, so which is this one right here, what is going out from the top, which is this one, and what is going out from the bottom. So these are in parallel. So we get R equivalent is 0.054. Just like the current circuit, this R equivalent will be lower than any one of those. Okay. Okay, so the Q total would be the total delta T, which of course is the same. Here inside 80, and this is 25 with its top or side or the bottom. So this is the total delta T, and this is the equivalent resistance here. So the total heat loss would be equal to around 1 kilowatt. Okay, just like the electrical circuit. We can find out the individual heat loss here. This is the delta T divided by 0.072 for this is the heat loss from the side, 764 watts, and heat loss from the top is 0.43. 128 watt here, and heat loss from the bottom is around 120 watt here. So as you can see, maximum heat loss is from the side. So we need to do something if we want to reduce or minimize the heat loss from the reactor. So this is just basically a concept of parallel thermal resistance, and we have seen the concept of series thermal resistances here. And finally, for the problem, we say this A is the correct option.